Welcome to AI for Good, the leading, action-oriented, global and inclusive platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker.
Thank you, Anna, for introducing the session. A very good day to everyone. Thank you for joining. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Jiaying Meng from ITU, the International Telecommunication Union. Today, we are having another interesting talk titled Foundation Models for Wireless Communications and Sensing. This talk presents the architecture, the self-supervised pre-training approach, and the training datasets of large wireless model LWM, the world's first foundation model for wireless channels. Meanwhile, our speaker will introduce an ITU AI and Machine Learning 5G challenge, where participants are offered a baseline LWM foundation model, 5 downstream tasks, and training sets. The objective of the challenge is to enhance the overall score across the 5 tasks. But before officially kicking off the session, I would like to introduce our esteemed speaker, Ahmed Al-Hatib. Ahmed is currently an assistant professor in the School of Electrical, Computer, and Energy Engineering at Arizona State University. His research interests lie in wireless communications, signal processing, machine learning, and applied math. And my colleague Vishnu, who will be taking care of the Q&A session. Now, without further ado, I would like to pass the baton to Professor Al-Hatib. Professor, the floor is yours.
All right. Thank you very much for the introduction, and thanks everyone for joining. Let me maybe share the slides and start. All right. I guess you see the slides. All right. Yeah. So excited today to give actually my first talk on foundation models for wireless communication and sensing, and in particular, large wireless models and how they are very efficient in learning universal representations that could be used to enable many interesting wireless communication and sensing tasks. So this is joint work with my PhD and former postdoc researchers, Sajjad Ali Khani and Goran Sharan. And this work has been supported by NSF and a number of industry grants. All right, with that, we start with the motivation. So if we look at the current communication and sensing systems in wireless, there are many interesting trends. 2 of these key trends are the use of large antenna arrays, which enable spatial and beamforming multiplexing gains and beamforming and spatial multiplexing gains in communication, but they also provide high spatial resolution for sensing. And they take different forms from massive MIMO, maybe at low frequency, millimeter wave, sub-terahertz, cell-free massive MIMO, reconfigurable intelligent surfaces, are all just different ways of leveraging large antenna arrays. And another trend is increasing dependency on higher frequency bands, going from sub-6 GHz to upper mid-band and millimeter wave and sub-terahertz. And with a higher band, typically we have more bandwidths, which enable also larger and better range resolution, higher range resolution. All right, so if we look at these 2 key trends in communication and sensing systems, so they are, again, mainly motivated by the interest in increasing the data rate and achieving better sensing capabilities and spatial range and so on. But then they come with challenges. And in order to really realize the gains of these interesting technologies, we need to address these challenges. So one of these challenges is difficulty in supporting mobility. So as we have larger antenna arrays, it becomes the channel dimensions become larger, and then they need more resources to estimate the channels or adjust the beams and so on. So which makes it hard to support mobile applications. Another challenge is that as we go to larger antenna arrays and also higher frequency bands, then robustness and reliability maintaining them becomes challenging. For example, if we have large antenna arrays and then we typically end up with narrow beams that any little movement for the users would affect the robustness of the link. And also, as we go to higher frequency bands, the links become very sensitive to blockages, and that could easily block and abruptly disrupt the link. Another challenge is that as we go again to higher frequency bands and larger antenna arrays, then typically we cannot just keep increasing number of RF chains. We need to do maybe analog or hybrid analog digital architectures at the RF front ends, and they come with limited, so they reduce the observability of what happens at the antennas in the baseband. And this comes with kind of complicating this results in some complication on the signal processing for different tasks. Another challenge is increasing power and cost, power consumption and cost as we go also to larger antenna arrays, especially at the UE, and that maybe need to continuously search for beams, which consumes a lot of power. Also, this increases the cost of the overall system, both in the deployment of the infrastructure and the devices. Okay, so many interesting challenges. And in order to address these challenges, machine learning was proposed in different ways to address some of these challenges in one way or the other. So briefly, I will talk about some of these interesting machine learning frameworks that have been developed in the last 6, 7, 8 years. One of them is channel mapping, which maps channels between antennas. And this is this concept or theory has been basically the foundation for many of the interesting applications that we see, like uplink to downlink channel prediction to channel tracking, spatial temporal beam prediction, or in sensing activity recognition, presence detection. All of these interesting applications, you can, when you use deep learning models to address them or to learn this mapping, you can actually ground the foundations back to this channel mapping concept. Another interesting machine learning gain is in learning efficient representations. And this finds a lot of interesting applications in communication sensing, again, like seaside compression, where we try to compress maybe the channel in small dimensions so that we can reduce the feedback overhead from the users back to the infrastructure. There are also other interesting applications that leverage this representation learning in beam codebook learning, in channel charting for localization, and sensing activity clustering. So many interesting machine learning frameworks that have been developed to address these challenges. But then a common limitation or challenge in these machine learning frameworks is the need for data, and many of them need labeled data sets. And so in order to really realize the gains of these interesting machine learning frameworks, we need to have large labeled data sets. And it's not just labeled data sets, but also as we go to practical situations and practical environments and realistic systems, then in order to these machine learning tasks become really complex. And in order to really learn and efficiently achieve the objectives of these machine learning tasks, we typically, again, need large labeled data sets. We also need to carefully design complex and non-trivial model architectures to deep learning model architectures to be really able to learn these complex mapping functions, for example, or to learn these representations. And also, we typically need to do a lot of hyperparameter for the optimization for the training parameters in these neural networks in order to really improve their performance. So all these are challenges, and particularly the large data sets that are typically very limited in many applications, and especially if we are talking about site-specific learning that would leverage data from each site. So every site would need to have, we will need to collect labeled data. So it's hard to scale to large data sets. So how do other machine learning fields or areas address these challenges? One key application or one key framework for addressing these challenges is through foundation models. And the key idea of foundation models is that if we have maybe different tasks, and these tasks, we only have small data sets, small labeled data sets for them, but maybe we have also large unlabeled data set. For example, in speech, we may have large data for speech, but then we have little data for speech and their text, right? Their corresponding text. Or in or in vision, maybe we have a lot of images, but then we have limited data with labeled images, for example, in classifying this as maybe cat or dog and so on, different classes. So how can we still do these maybe challenging machine learning tasks that need this labeled data set, but still, while we have small data sets for the labeled part, and then leverage these large unlabeled data sets. So the main approach that is that we see in other areas or in other machine learning fields is through foundation models. And the idea here is that we use this large labeled data set to train, or to be more accurate, to pre-train foundation models in typically self-supervised way to learn universal features and embeddings and representations and patterns in these data sets, in this labeled data, in this unlabeled data. For example, from speech, from images, from text, and so on. And then once we have this powerful feature extractor or embedding or representation extractor model, foundation models, then we use it to serve the different downstream tasks. In that way, for example, we have, let's say this is an image classification task. Now we have this foundation model that is trained just to understand different embeddings and different features from the images. Then we get this small image classification data set, which has the image and the corresponding class. And we first feed the image through the foundation model to get the embeddings. And then we train the downstream model based on the embeddings of this foundation model instead of training this downstream model based on the raw image. Okay, so essentially we train, the key point here is that we train these downstream models based on the embeddings of the foundation models instead of training them directly on the raw images in this particular example. And then typically when we do that, then this results in interesting consequences. First, it typically reduces the amount of data that we need to train to learn these complex tasks that need labeled data. And then it also simplifies the model architecture. So typically these downstream models could be massively reduced in terms of complexity while still achieving these objectives. And also it typically simplifies the training hyperparameter optimization that we need to do. So it makes basically the downstream model design and optimization much, much simpler and much more efficient from compute latency perspective and so on. We can also, so this is one way. Another way is to also use this limited data to even fine-tune the foundation model plus the downstream model end to end, so that then we end up with a foundation model that is fine-tuned for this particular task and is very good in this particular task. So that's why maybe we have one foundation model, but then it gets fine-tuned on many tasks to have like basically different variants eventually of this foundation model. And we see this in, for example, in text and image and computer vision and in other areas. All right, so if we look at very quickly on other areas, we see in text or natural language processing, NLP, BERT has been the first widely used or recognized foundation model. And it is basically the main BERT architecture was pre-trained on a large unlabeled dataset from Wikipedia and book corpus. And then once it is pre-trained, then it gets used to fine-tuned to do different tasks, question answering and text classification and so on. Similarly, in speech, Wave2Vec is one of the main and first foundation models that it's again based on transformer, and it is pre-trained on large data sets, hundreds of hours of speech, but again in a self-supervised way. And then once it is pre-trained, then it can be fine-tuned to serve different tasks that again have limited data, like automatic speech recognition, speaker identification, and more. And in computer vision, VIT is, or Vision Transformer, is one of the main and first widely recognized foundation models. And again, it's based on transformer encoder architecture and encoder architecture. And then it is also pre-trained on massive data set from images, and again in a from ImageNet, 14 million images, and there are actually different models. but one of them is trained on 14 million images from ImageNet and 300 million images from GFT, which is a closed actually data set in Google. But then once it is pre-trained, then you can fine-tune it for many tasks such as image classification, object detection, and so on. All right. So basically what we did last year is we said, okay, we have all these interesting foundation models in different areas that are used to serve exactly the same concept or challenges that we face in wireless. So that's why we were motivated to build LWMs or large wireless models as foundation model for wireless communication. And the first release of LWM, we were focused on channels as inputs. So basically, we feed the wireless channels and to LWMs, and we train or pre-train these LWMs or these large wireless foundation models in a self-supervised way to learn how to reconstruct the channels, essentially. And I will talk a little bit more about this, but in a way that doesn't need any labels. And then once these LWMs are pre-trained, so they essentially learn how to extract universal and important and useful features from these wireless channels, and then they can be fine-tuned to serve different interesting communication tasks like line of sight, non-line of sight classification of the channel. So for example, if you have a new channel, I mean, does it correspond to a line of sight link or a non-line of sight link? Can we use it? We can use it also to do robust beam prediction or to map to get the channel maybe in one frequency band and predict the beam in a different band. So that's what I mean by beam prediction here. It's not that you take the same channel and predict the beam from the same band, and because you probably don't need machine learning model to do that. Channel estimation or denoising. So if it is very powerful in learning how to denoise channels, because essentially they are, as I will talk a little bit more about this in a few slides, they are by extracting features and then reconstructing the channel again, this can act as denoising for the channels. They are also very interesting and very powerful in channel interpolation. For example, if we have missing subcarriers or missing antennas in the channels, can we reconstruct them or interpolate and extrapolate them? They're also very powerful in localization and then also in different sensing tasks like presence detection, activity recognition, gesture recognition, biomarker sensing. All these tasks rely on analyzing channel data, in that case, sensing channel data. So these LWM models could be fine-tuned for these wireless sensing data to basically help to address these tasks. And we're also releasing very soon other variants of LWM, like LWM Spectral, which focus on taking the spectrograms of received signal as input. And then this could be used to basically serve or enable other applications that require not just analyzing the channel, but also the channel jointly with the transmit signal. So it could be used to do modulation classification, signal detection, and in sensing, they could be powerful in doing gesture and activity recognition without explicitly estimating the channel. So we are very excited about LWM and what it could enable, and briefly talking about the architecture. So the LWM architecture overall is somehow similar to the VIT, where we adopt the kind of the general framework of we divide here the wireless channel into batches, and we do some masking in the training. We developed a particular approach for this masking that is specific to wireless channels, that basically account for the special characteristics of the wireless channel as basically which are different than other areas. But with this masking, so basically we have the channel, we divide the channel into batches, and then once we have these batches in the training phase, we mask some of these patches, and then we do patch embedding and positional encoding, so that we preserve the positional information within these different channel patches, and then we pass this through a transformer encoder that is generally similar to the standard transformer encoders that are also used in VIT and BERT. And then once we get the embeddings of or the output of this encoder, we feed them in the training. We feed them to basically a simple network for decoder to reconstruct the channel, and then we train this end-to-end in a self-supervised way to learn how to basically extract the interesting and important features and embeddings that kind of recover these missing patches or the masked patches from the context and of the full channel. I will talk a little bit more also about this in the next slide. But essentially, this is the general architecture. Now, once this model is pre-trained, then when we start using it, we basically throw away this decoder, and then we just use the encoder directly with downstream tasks to serve different tasks. Right? You can have multiple now downstream models to serve different tasks. So the general structure of LWM is similar to VIT, but the pre-training strategy is actually more similar to BERT that we adopt. And as I mentioned, we developed this masked channel model for real imaginary channel patches that are specific to wireless channels. Now, a key, of course, part of developing a foundation model is to train it on large amount of data so that they can learn these universal features efficiently that are generic and generalized across tasks and across environments. So with this motivation, we used, let me try to hide this. All right. So with that, we used DeepMIMO and in particular 15 scenarios from the DeepMIMO dataset. And they correspond to more than 1 million channel samples. And they cover different number of antennas and subcarriers at the base station. They are also, and of course, different cities. And so that's why we think this dataset has sufficient diversity to learn these important universal features across different environments and tasks. Now, of course, this is something that could be developed more and more. So we are, and I will talk a little bit more about this in the competition when I talk about the competition in a few slides. Now, if you are interested, what we also are offering as part of LWM, so the LWM model is open source. It's available on Hugging Face and also on the website of the LWM, lwm-wireless.net. We are also offering a script that it basically fetches all the scenarios that we used in the training here from DeepMIMO using some APIs, and then it do all the pre-processing and generates the AI-ready dataset for training the LWM. So if you want to kind of retrain even the LWM from scratch, we have the script that takes the data, organize the data, and do everything to make this kind of very smooth process. All right, so the pre-training strategy, again, of the LWM, I talked a little bit about it. So we focus on the decoder. When we reconstruct, we try to mask some of the patches of the channel, and then train this model end-to-end in order to learn how to, in a self-supervised way, how to recover this masked channel with contextual channel reconstruction. And especially from the context, it tries to learn what are these missing channels. And by doing that, it kind of implicitly learns deeply some of the spatial and spectral and temporal dependencies between these different channel patches, right? And this is kind of a key in, of course, wireless channels. Now, once this model, LWM model is trained, and what we are offering till this point is two models, LWM 1.0 and 1.1. 1.1, of course, is much more capable and trained on more data set, and it's a little bit bigger. Once these models are pre-trained, now you don't need to pre-train them again, right? So you can just take this pre-trained, so download this pre-trained LWM model from Hugging Face, and then you can say you go now to a new environment. You have certain tasks, say localization or channel denoising. This is a typo here, sorry, or channel interpolation. Then what you need to do is to go to this new site, collect a small data set for this particular task, and then download the LWM model, take the channel. So this labeled data set will have the form of channel and the corresponding label, for example, location or line of sight, non-cell class, and so on. And then you will feed these channels to the LWM foundation model. You will get the embeddings, and then you will train the downstream model based directly on these embeddings. So for example, when I have this embedding for the channel, that was the corresponding line of sight, non-line of sight class, and so on. And then this typically, again, as I mentioned, leads to less data needed for the training, less model, simpler model architecture, and less training hyperparameter optimization. We are also encouraging benchmarking and ranking of these models. So, if you develop any variation or variant of LWM, for example, if you take the LWM model and fine-tune it more for certain tasks, or even change the architecture and pre-train it on more data and so on. And if you are interested in listing your model with your paper on the LWM website, we would be happy to assist with that. So the hope here is that we'll have basically follow the other communities, and we'll have ranking tables with many foundation models in wireless with their corresponding tasks and what they enable. All right, now I will talk a little bit about some of the applications, just example applications. I mean, and some very initial results actually from for these applications for LWM, and then this will also motivate for the competition as I will proceed. All right, so we looked at many applications for LWM. 5 of these applications are line of sight, non-line of sight classification, and we have actually an online demo also on Hugging Face that you can play with. For line of sight, non-line of sight classification and beam prediction, sub-6 GHz channel to mmWave beam prediction. So in line of sight, non-line of sight classification, again, if we given the channel, can we know whether or not this channel corresponds to a line of sight or non-line of sight link or user a channel. In the sub-6 GHz channel to mmWave beam prediction, here this is motivated by dual band systems that would operate probably at 2 bands. And sub-6 GHz in the sub-6 GHz band, it's easy to acquire the channel, but in mmWave, it's very hard to design the beam. So if we know the channel, the sub-6 GHz channel, can we predict what would be the best beam at mmWave, which is a different band? So this is one of the interesting applications for machine learning in literature, and we kind of revisited this problem now with LWM. We also looked at user localization and channel estimation, in particular denoising, and channel interpolation and extrapolation. And the way we were looking at this, essentially, we wanted to see really how much gain we can get, and if we are going to get any gain from LWM or this foundation model compared to the state of the art in these different problems. Now, the state of the art models have been very carefully designed and optimized and tuned right from the model architecture to the data to the hyperparameter training. Now, what we did here is very simple. We took the LWM model. We looked at 5 data sets for these 5 different tasks, and then we inputted. We compared 2 cases. First, if we use LWM, so first we feed this limited channel data to the LWM, and then use the embeddings of the LWM to train the downstream model, for example, for these 5 tasks, one per task, of course, without any special hyperparameter training. So we didn't even try to optimize hyperparameter training parameters of these downstream models in the LWM case. And then we compare this with the case when we use basically the state-of-the-art models from the literature for all these 5 tasks. So again, these models are typically much more complex models and much more optimized from training. One thing I forgot to mention, for LWM, the downstream model was very simple. If I remember correctly, just two fully connected layers. So it's very simple and trivial architecture. So these are the downstream models from the state of the art that we considered. So a CNN for line of sight and line of sight classification, complex fully connected network for sub-6 to mmWave beam prediction, and for channel interpolation. A complex CNN and data with a lot of data processing for the channel estimation denoising, and for localization, we have this complex fully connected network with a lot of data pre-processing. All right, now, as I mentioned, typically these models are complex models and fine-tuned and optimized significantly for this particular task and for this particular data and scenario, which also makes them kind of tend more to overfit with limited data. So if you train these models with limited data, typically they overfit. And this is a challenge. If you have a complex task, you typically need to design a complex machine learning model to learn this complex underlying function or relation or whatever you are trying to learn in this task. But then this complex model will also need a lot of data, right? And if you have limited data, then if you train a complex model with limited data, typically this model overfits. And this is what also the LWM address. Okay, and these are the initial results that we obtained across these 5 tasks with LWM. Again, by just passing this limited data, here we have a small data set of 200 data points that, I mean, for the 2 cases, for LWM with and without LWM. And again, we train these downstream models, this very simple downstream model for the LWM case, or the complex models in the and without LWM for the state of the art. And then we compared the performance. And this is what we got. So if we, again, with this limited data, this is the best we can get with these models, the state of the art. And if you use LWM, we get this gain. So again, in some cases, it is relatively small gain. In other cases, it's higher. But again, we got these better gains with very simple downstream model design, with very simple training, without almost any hyperparameter optimization. So there is huge gain, I think, and huge room for optimization of this gap. And this is exactly what we are excited about in the machine learning competition. So that focus also on these particular 5 tasks. So, and we're excited to collaborate with ITU in offering this new machine learning competition this year, which actually the registration just opened for it. And the general idea is kind of based on what I mentioned, is we are offering 5 tasks. I will talk a little bit more about them also in the next few slides. But the general idea is that we have 5 tasks. We want to see how much gain you would obtain through the LWM by optimizing the LWM model with jointly or disjointly with downstream model architecture to optimize the performance of or the scores of these 5 tasks as much as possible. So in more specifically, we participants that register in this competition will be provided with a baseline pre-trained LWM 1.1 model, and also will be offered or provided with 5 downstream model baseline downstream models for the 5 downstream tasks, and will be provided the limited training and test set for the 5 tasks. And these 5 tasks are also the 5 tasks that I just mentioned: line of sight, non-line of sight classification, beam prediction, CSI interpolation, estimation, and user localization. And the objective is, given this baseline LWM model and baseline architecture, the participants can have actually a lot of freedom in what they can do. So they can optimize even the training of the LWM by training the foundation model on more data. And by doing that, they can maybe hopefully get better LWM, better foundation models, and better feature and embedding quality. They can also, and I'll talk more about also the data set that we are kind of opening for participants to help them kind of towards this objective. They can also just even change the architecture or optimize the architecture of the LWM to achieve better results. And they can also optimize the downstream model architectures or training parameters. And they can also fine-tune them end-to-end, right? So they can optimize one LWM model per task. So they can end up with 5 fine-tuned LWM and downstream model combinations for the 5 tasks. So that's also possible and allowed in this competition. And to basically enable this more, we will give all participants in this competition early access to DeepMind v4. And DeepMind v4 is a dataset that we have been working on, and we hope to release it soon as well. So DeepMind v4 offers datasets from Wireless Insight, Remcom Wireless Insight, and as well as NVIDIA Shona. And then hopefully soon also we'll have more data from Aerial SEM, which is another digital twin simulator from NVIDIA. And maybe what's interesting is that now in DeepMind v4, we have hundreds of datasets. So just to give you some sense, so in the foundation, in the baseline foundation model 1.1 that we are providing to participants, we have only trained it on 15 scenarios. So in this DeepMind v4, participants will get access to more than 200 scenarios. So there is hopefully huge room for optimization here and realizing more and better and more interesting foundation models. All right, so back to the competition. Basically at the submission stage, the participants will submit the optimized model, foundation model, LWM, and the optimized downstream models, as well as the training parameters that they used in the training of both of them, and also will submit the scores across these 5 tasks on the test set or the challenge set that we will offer at the submission stage. And then we will evaluate. So for every task, we have a score from 0 to 1. We normalize all the scores from 0 to 1. And so these are, for example, the baseline scores, and we hope to get to that participants, of course, will end up with much better score for these 5 tasks. We will of course evaluate based on the composite score across the 5 tasks. So all of them are from 0 to 1, so it's easy to basically average and get a composite score for the 5 tasks. So registration is now open for this task. If anyone is interested, or if anyone knows also students or other participants who could be interested, please share this with them. And the final models, as I mentioned, will be ranked on the LWM website along the papers, of course, so anyone can use them and can cite your papers. All right, to conclude, complex machine learning is interesting for many tasks, but then in reality and in practice, many of these tasks in communication and sensing are challenging and are complex tasks that require large data sets that are really to realize the gains of machine learning. Typically, we see much gain with site-specific data, but this data is typically limited. And also we need typically to have very complex model architecture design and training optimization. LWMs or foundation models try to address these challenges by first having a foundation model that is pre-trained to learn universal feature extraction, universal features and representation and patterns, and then by fine-tuning and using these embeddings to serve the downstream models. Typically, this ends up with much limited data or much less data needed, lower complexity, and more kind of simpler downstream model training. And LWM supports many interesting applications in communication and sensing. We will be releasing versions of LWM soon that support different types of inputs. And registration for the competition is open. DeepMind website, you can check for more of these datasets. And if you're interested in getting early access to DeepMind v4, also please let us know. And if you are interested in learning more about LWM, you can check the LWM Wireless website. With that, I conclude. Thank you very much, and looking forward to any questions.
Thank you very much, Ahmad. I think that was wonderful talk. I remember our discussion during, I think it was 2 years back when we discussed a similar challenge and data sets. And yeah, it's very satisfying to see the progress which you have got.
Thank you.
I think this is a very exciting challenge. Yeah, thank you very much. It's a very exciting challenge. I'm very excited for all the participants as well. First question, which I think is in the minds of the participants, and I think that is an important question, is the synthetic data set. So I think in that beautiful slide, this one. So this is really beautiful slide. So here at the bottom, you have Shona. Shona is actually one of our colleagues from NVIDIA, had talked about it in the previous workshop that we had as well. And the others which are here as well, they point to that. But can you explain, like, if I'm a participant, can I use one of these tools, use synthetic data sets for the fine-tuning, please?
Sure. Thanks, Ocean. This is a very good point. So let me clarify this more. So we hope actually that these LWM models are kind of as part of this competition, participants get access to more and more and more data set and train them much more to be much more capable. We think that what we have now are really baselines, LWM 1.0 and 1.1. We looked at them as initial steps. I think there is huge room for optimization. So participants can train these models more, pre-train these models more on synthetic or even real data sets, right? So maybe some participants will have access to open source or closed source real data sets that they can train these channel data sets, right? Or that they can train these LWM baseline models on, or they can also use synthetic data. So on the synthetic data side, we are offering access to DeepMIMO v4, which we hope to release soon. So in DeepMIMO v4, we are doing a few things, but two of them are we are unifying the DeepMIMO, the output of the ray tracing simulators. So meaning that we have, as I mentioned, more than close to 200 data sets, DeepMIMO, what we call DeepMIMO datasets or scenarios. And these datasets some of them are coming from Wireless Insight, some of them are generated by NVIDIA Shona ray tracing. But the good thing is that they are in the same exact format. So that so that participants basically can just use, if they have codes that use a DeepMIMO generator to generate datasets, DeepMIMO datasets, so they can mix and match scenarios from these 200 datasets, right? From also that are coming from different ray tracers. And this makes it richer, right? That you have now multiple ray tracers, multiple parameters that generate these 200 datasets, and then you can merge them all, select some of them, and so on, and choose the parameters in the DeepMIMO, for example, the number of antennas, so this adds another layer actually of diversity. So even with these 200 datasets, you can generate many more datasets by tuning these parameters, right? You can change the number of antennas, the number of subcarriers, antenna orientation, and so on. And then this basically multiplies these 200 raw dataset DeepMIMO scenarios by by certain number to get even more AI ready datasets for training the model architectures. Does this clarify it a bit?
Absolutely. Yeah. Thank you very much. I think the twin question, the related question, which I believe many of the potential participants who are listening would have, is about compute. So we discussed this, during our preparatory meetings also, that what kind of compute is required. Actually, in slide 19 or so, you did explain what are the tasks which are expected or potential tasks. I think there is a lot of freedom, but I think you explained what are the potential downstream tasks are possible. So I think it was slide 19 or so, which had that.
Sure.
So what I want to ask you is that for this kind of task, what are the compute requirements which are possible? Which are needed, needed. And for example, if you want to fine tune the LWM or look at the 200 data points that you have, or synthetic data sets which they generate, what kind of compute is required in your experience? Yeah, please.
Great question. Yeah, great question, Vishnu. I should have maybe clarified this more. So we think like there, I would say, different options that participants can do also many of them. But one is they can maybe just use the baseline LWM models that we provide, and just optimize as much as they can the downstream models, right, to optimize the end-to-end performance. So that doesn't need much compute at all. One thing that I wanted to highlight here is I have one of these slides in the backup slides. So the model, it's called large wireless model, but it is actually not as large as LLMs, for example. So the number of parameters in LWM 1.0 is 600,000 parameters, and 1.1 is 2.5 million parameters. So it's kind of much more reasonable compared to a billion parameters and LLMs and so on. So if the participants want to just optimize the downstream models, and these are could be much simpler models, because as I mentioned also, once you use the LWM embeddings, this gives you the opportunity to even reduce the complexity of the downstream models a lot, while with compared to just using the downstream, just optimizing downstream models trained on raw data. So that I don't think it requires any kind of special, like just very simple GPUs. I think will be the very basic ones. I think will be more than enough. The second thing is, if you want to now fine tune the LWM with the downstream models end to end. Okay, so that also I think is very reasonable, because the model complexity, the LWM model complexity is just, as I mentioned, a few million parameters. So fine tuning this end to end is also on fine tuning. Of course, I mean fine tuning on the limited data that we are offering for the downstream model, right? This is, I think, or even if you have access to a bit more data, and this doesn't need a lot of data. So just to fine tune, so that could be also very reasonable from compute perspective. Now, the third thing is, if someone wants to actually pre-train the LWM really on these 200 data sets, right? So that would require more compute. But this I think like it will be in the order of a few GPUs, right, for a few days or something. So that's maybe cloud GPUs for a few days. So I think that's kind of the range that it's not like a cluster of 100 GPUs for for 2 months or something.
Thank you very much. Yeah, I think this looks possible. And just for the benefit of participants who are wondering, ITU does provide compute. In fact, for this competition, we have compute allocated also. So if in case you are short of compute, let us know. I mean, you won't be disappointed. Lumin is asking, thank you for the great presentation. Can you please make more comment on the CLS? I think it was on slide 16. I think it was quite clear in your slide 16 that, this one. So we did discuss this, actually, CLS embedding during our preparatory meeting as well. We were discussing.
Yes.
Can you explain a little bit more why CLS embedding and this particular relationship that you have shown here as well? Yeah.
Mm-hmm. Yeah, sure. So the CLS token is those who maybe not very familiar with this architecture. So basically, you can add the CLS token in the training, and then there is also CLS embedding. So CLS embedding, you can think of it as a very small dimensional vector that somehow summarizes these features and patterns very well of the input and these representations very well. So in some cases, they could be good, especially in classification tasks. They are very powerful in classifying. So basically the advantage here is that they are very low dimension, which could help a lot in the downstream tasks. So we have seen, for example, in localization and in line of sight and line of sight classification and in beam prediction, we saw very interesting gains if we use just the CLS tokens for classification compared to, probably we don't need to use many of the other embeddings. In other tasks, actually like channel denoising, we saw a need to use the rest of the embeddings, giving much better performance.
Thank you very much. I think in slide 22, yeah. Yeah, so this is an interesting slide. So I think with very minimal, I think 200 points or so, you have beat the state of the art. This is really interesting. I think this also we discussed. So in your mind, what is the best case scenario? So the best case scenario, I can imagine that some of the participants are able to clearly beat this. You also mentioned huge potential for improvement. So I'm guessing that maybe with the fine tuning, either from the LWM or with the data sets, we are able to clearly beat the state of the art and this one, what you have baseline. Is that the best case, or there are more? You are expecting newer architectures to come out, or something really out of the way. What are your best cases scenarios?
From like improvement, like
Yeah,
tooling.
yeah, yeah.
Yeah, sure. So, but first, just to clarify, so here we are training the downstream and the LWM downstream models, right? Based on these 200 data points. And this is like really the regime where we see most of the gain, right? Like if you have complex task and limited data. So this is where we see like a big gain typically from LWM compared to baseline. Now, if you once you have a lot of data, a lot of labeled data, then yeah, then probably you just can train your downstream model right away. You still actually get these advantages of simplifying the downstream model architecture, even if you have a lot of data. You need to do a lot of like complex model architecture, right, to be really able to get good performance and a lot of hyperparameter. So that this gain stays even if you have a lot of data. But just to clarify, so that here, I mean, for a fair comparison, we are basically comparing the two when we have limited training data sets. Now, from improvement perspective, I think really there is a huge gain. We honestly didn't do much optimization for, I mean, and intentionally maybe because we wanted to also like African's baseline architecture, but I think there is huge gain for optimization here. And for example, in some of the tasks we are looking at 60%, right, score. So I think there is huge optimization here to improve this. And I think a lot of this optimization could be obtained by fine-tuning these model architectures more, these models more, and the LWM models more, and fine-tuning them end-to-end with the downstream models. Also, by playing with the hyperparameter training for the downstream models, by optimizing the model architecture. Again, we just used two or I think or three simple fully connected network for the downstream models in the LWM case. Right. So I think there is a big gain for improvement by, being also more innovative in the downstream model design. And then I think also, honestly, I think there is huge gain for optimization by pre-training this LWM model or fine-tune it more on more data, just as a foundation model, right? So I think what we have, as I mentioned, is just initial versions of these LWMs. But I think as and we have seen this from LWM 1.1 to 1.0 to 1.1, we saw like clear gain in some tasks. So going from 600 parameters to 1.3 million parameters, and going from or 2.3 million parameters, and going from the training set from 800 to 1 million. So it's kind of just so this 1 million actually, I mean, the reason why we didn't increase the data set here much is because we also were interested in increasing the variations of the input, number of antennas and number of subcarriers. So we wanted to make sure we don't have like the same channel sample realized in different number of antennas. So to really ensure like kind of credible kind of training. But yeah, I think as we increase the number of data sets for retraining this model, I think we can get also a lot of gain.
Thank you very much.
I think
think
if participants have access and to kind of some compute and then took this and train it on
Mm.
a 100 deep data set, I'm sure, I mean, there will be and also increase the size, the capacity of the model, I think there will be big gain as well. My intuition.
Yeah, thank you. Yeah, I think that's actually the deep MIMO dataset that you mentioned. That can really, in my opinion, that's a game changer. So the early access that you mentioned, that itself is quite interesting in my opinion. When is it coming? I mean, just to put you on the spot, when is it expected to come?
To kind of be released completely.
Yeah, I mean, for the participants,
for participants, it's ready now for early access. Actually, I mean, and actually, also if anyone is interested from the audience to get early access, please send to us. I mean, we'd be happy to. I mean, it's now in kind of testing phase, so alpha version, but we hope to release it completely by sometime in like maybe towards end of June.
Okay, thank you. That is quite interesting. I think we will be looking forward to playing with that as well. Maybe the last question that I want to ask you is, you have had we have had you here previously, and we have had this progression from previous competitions as well, and data sets as well. I mean, you had explained data sets as well. What is the approach that you have taken? I mean, I can guess, but at the same time, for the benefit of the audience, what is the progression of research that you have seen? I think we have engaged probably for last 3 years or so, I think. And so can you explain how we got here? What is the thought process and how did we get here, please?
From dataset perspective?
Yeah.
So this is interesting question, Vishnu. So, well, I mean, I think one key motivation for DeepMind v4, there are actually a few motivations, but maybe 2 or 3 of them are one, scalability. So, to the best of my knowledge, so this would be the first opportunity that we can very easily. I mean, we have APIs actually for DeepMind v4, so all APIs you can, from the Python code, you can search even the database of datasets, download the datasets that you are interested in. You can filter based on features and so on. We are also adding features to every dataset. Is it like, for example, things like labels, like is it rural, is it suburb, whatever, is it how many reflections, scattering, and so on. And so we are adding a lot of features. So you can download tens of datasets, maybe hundreds, and train your model right away, right? So on hundreds of datasets. So, and this process of searching and downloading, so you don't need to go now manually to the website and download everyone, right? So you can do everything from APIs, and then you can scale, right? So scalability so now you have the opportunity really to train your machine learning model and evaluate it based on hundreds of cities, and the data preparation part of that could take just tens of minutes. So just to download this data set and just prepare it, this is probably tens of minutes. Now the training is a different story, but just to get that access to data is so so that's kind of scalability aspect of and now you can do a lot of things. Like if once you have access to a lot of data, you can now maybe study where are the regimes where my machine learning model works well, which regimes it doesn't work well, does it generalize or not, does it, right? So you can study a lot of interesting now kind of robustness and scalability questions and problems, right, within this. So that's one thing. Another aspect is this is also a community data set. We put a lot of effort in actually DeepMind v4 in making it kind of really hopefully useful and feasible and easy to use and easy to contribute to. So in DeepMind v4 we are opening source the converters from the ray tracers to the DeepMind format, meaning that if any researcher develops has access, say, to Wireless Insight, and they already generated a data set using Wireless Insight, generated some scenario using Wireless Insight. Now using the open source converter of DeepMind, and then in one line of code, they can call this function. It can go to the folder with the output of the Wireless Insight, parses the files, and prepares a DeepMind compatible data set. right? That they can then, with another line of code, also upload it to our to DeepMind with their paper. So they can say, okay, this is whoever uses this, then whoever uses basically their scenario, they need to cite their paper. But this is now kind of fully automated and fully possible. So yeah, so kind of enabling also community contribution. So we hope this 200 data sets that we have now hopefully will grow more as the community starts to contribute more. And then kind of this also enables benchmarking and now comparisons between data sets and also between ray tracers. So for example, one of the other things we are also doing here is to support more than one ray tracer from Remcom and NVIDIA, Shona, and also ArielSam, which is hopefully coming very soon in June. So now imagine you have the same scenario ray traced in 3 different ray tracers, right? And you have now access to these 3 DeepMind scenarios. They're all the same format, but they're coming from 3 different simulators. Now you can study also your machine learning and see how it performs across all of them, compare and so on. So yeah, so these are some of the objectives I would say that we had in DeepMind v4. We have also much more actually optimized generator, more efficient structure for the data. We are also, as part of this, actually, we're also supporting linking or interfacing DeepMind with multiple system and link level simulators like NVIDIA link level simulator, Enter Digital. They have also an interesting link level simulator called NeoRadium, which we already actually integrated, and we have been working with them closely on that, and MATLAB 5G toolbox. So yeah.
Wonderful. Yeah. Thank you very much. I think we will hear more from you during the workshop. In fact, Ahmed is a confirmed speaker for the workshop in Geneva as well. So thank you very much. Thank you very much, Ahmed. This is very exciting. Best of luck for the participants. And thank you for explaining all the questions. Back to you, Jay.
Thank you very much.
Thank you, Vishnu, for the Q&A session and Professor for your contribution during the whole talk. Now, I'd like to thank everyone who participated in the webinar today. Please note that our challenge is now open for registration and participation. The link to the challenge is posted on the video wall. You can now start working on the solutions and submit the results on the portal. Several prizes and certificates are planned to be handed out to the winners of the challenge, and free computes and GPUs will be provided based on needs. We have more sessions in the future, so please check the AI for Good program page for more details. We look forward to your submission. Thank you for joining. See you next time.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for good.